All right, so number 16, it says find a simple basic function as a right-hand behavior model and a simple basic function as a left-hand behavior model. So what they're saying is you've got two functions, right? And so for the left-hand behavior, we're talking about the limit as x approaches negative infinity. Whoops, not 8. Negative infinity, right? Now, if we're talking about the right end, we're talking about the limit of the function as x approaches positive infinity. And so what we're going to find is one of these functions will have a little bit more of a dominating effect as we approach positive infinity. The other one will have a similar effect as we approach negative infinity. And we could do this mathematically or analytically if we just think about this for a second. What do we know? What do we know is going to happen as x approaches a very large number? What's the first thing we could think about?
All the small numbers become unneeded.
Yeah, so like dividing by 3, if I have a trillion squared, right, and I divide that by 3, it's still a pretty big number, right? So I'm really multiplying by 1/3. That may or may not be significant, okay? Now, let's think about this. If I plug in a negative x value, then I'm going to get a negative x value here that's squared plus e to the negative x. Now, what is e to the negative x really? It's really 1 over e to the x. So now if I get a really, 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 really large negative number, it's the same as 1 over a really large number. Does that make sense? Yeah. So this goes to 0 as I approach. In other words, what I'm really saying is if I take the limit of f of x as x approaches negative infinity, this value here approaches 0. And what do we know about this value? What happens when you square a negative number?
It's positive.
Positive. So this becomes a very positive number. So this would be infinity, right?
Yeah.
So which one dominates in this case as we do the left end? And
Negative x squared.
yeah. So this one here would probably be x squared. I don't know. This is an arbitrary thing. Like you know that. You could divide it by 3, it may or may not make a difference, but usually we want to kind of choose a parent function. So I'm going to say that we probably won't multiply by 1 over 3. Okay? So for my left end behavior then, I'm thinking x squared. Now let me just try this again, but now we're going to try it with positive values.
Wait, so they're both x squared? Is the your answer?
No, one's going to model left end behavior, the other one's going to model right end behavior.
So which one is x squared? You put an arrow
X squared
right.
is for the left end. Okay. So now let's consider the limit of f of x as x approaches infinity. So this would be like your right end behavior. Whoops. If I could spell right.
I'm still kind of confused on why you already.
Huh?
I'm still kind of confused.
Oh, because it's insignificant, right? What's a billion divided by 3? It's 1/3 of a billion. But what's 1 billion squared divided by 3? Still a billion. It's a very large number. So as we approach infinity, multiplying something by negative 1/3 or multiplying something by 1/3 may be considered insignificant. I don't know yet. I'm just thinking out loud. Yes.
It's
I know. I still have to model the thinking process though, right? Okay. So it may be important. We don't know yet, okay? So I'll write it there just so you guys don't get confused. So now if we look at this, if I take the limit of this, what happens when I plug in a really large number into this one? A positive number. When I plug that in, what happens?
It's going to remain a large positive.
A very large positive number. Now, what about this one, though?
That's going to be a large positive.
That's going to be a large positive number. Which one do you think will grow quicker?
The
The one
square.
at the
I don't know.
E to
No,
the
the e
x.
to the x.
yeah.
Yeah, so think of it like this. This would be like if I were to plug in, if I were to do f of 10,000, right? That would be 10,000 squared, all divided by 3. And then this would be like 2.72 raised to the 10,000. Which number would be bigger?
2.02.
Yeah, this one would be, right?
And that's your
That's the expression that kind of dominates the graph or behavior. Does that make sense?
yeah.
So we could say, and Mr. Adams is just guessing, what would I do before I actually chose an answer? Graph them. I'd have to graph all three. Graph the original function, the total expression here, and then graph the two separate expressions. So I think the right end behavior should be e to the x. Okay? I don't know. So now if I look at this, I think D might be the answer. See, the problem is I don't see one that's just x squared, but I do see one that's x squared divided by 3.
Yeah.
Okay?
Wait, well, C is x squared.
Yeah, but it's got a e to the negative x, and that's not what we're looking for.
Yep.
So remember at the very beginning I said this dividing by 1/3, it may or may not matter. Apparently to the author of the textbook it does.
So the numerical value of the natural log is 2.72.
That's not the natural log, that's Euler's number E. Yeah, it's about 2.72.
Oh, Mr. Adams.
2.71, something like that.
So
Yeah.
on our test, you would take x squared or x squared over 3. Like if this
Yeah. So if I put this on your test and it's not multiple choice and you just wrote x squared, I'd be okay with it.
I'm so a little confused. Just like, I don't think I could do this
The
alone.
right end is the one on the right.
But not with that negative attitude.
Well, how'd you know which is right and which is left?
Well, because the right is the limit as we approach infinity. So if I graph this thing, right? If I approach, let me graph it. I'll show you. So the question that the student asked was, how do you know which one's left? How do you know which one's right? Which is really saying, Mr. Adams, you need to show me a visual on this because I'm not seeing it in my head. And then I would say, well, my bad. I'm a horrible teacher. I should have thought of that a long time ago. E.
It's because he's a band.
What? Okay, so that's what we need to do. So now if I graph this, you've got some behavior like that. It kind of just looks like a parabola,
But the
right?
right side goes up faster.
Yeah, but if you look, so here's what we did essentially. We did this. We said x squared divided by 3 would be the left-hand side. And then we said that e to the x would dominate the right-hand side. So now when we graph that, you see how the red one, see how one models the other? Does that make more sense now?
Yeah.
So we're going to use the red line. So this red line, this is actually x squared over 3. And as you can see, it kind of goes right along the line of the function, right? And then this one right here, this black line, this one goes right like this. That's my e to the x. And so what we have here is we have one function that kind of models the left end behavior, and the other one that models the right end behavior. But what does that mean with regards to limits? Well, this was because the limit of this as x approaches positive infinity, or I'm sorry, let me do it all the same color so you're not confused. When I take the limit as x approaches negative infinity, in other words, I'm looking at this blue line and going in this direction, it's the same behavior as this function. So I took the limit of x squared over 3 plus I took the limit of x squared over 3 plus e to the x, and it looks a lot like this if I look at the limit, right? Then what I did over here is I took the limit of x squared plus 3 over e to the x as x approaches positive infinity, and it looked a lot like this, right? Because this one maps up over there. Does that make sense? And so here's the thing, when I go to do like some sort of computer programming or some sort of modeling or calculating things, sometimes we're only interested in the end behavior and we don't care about what goes on in the middle. Well, for a calculator to calculate this expression, whoops, that's a little bit of work for a calculator to do. But I could have one calculator, let's say I'm only interested in the left end behavior. Then I would have if I was only interested in the left end behavior, then what I would do is I would focus and have the calculator just focus on this, because eventually they're going to be approaching the same values. Now if I come over here and I'm interested in the left side, then I would just have the calculator make this calculation, because those values would be basically the same. Does that make sense? Okay, cool.
So for this, you just kind of break the problem up in like into the two halves and choose yourself.
So a big field in computer science is dealing with the efficiency. Right now, because computers, the processors get hot for every calculation they make. So there's actually a field of science where you actually figure out how to make the same calculation in less steps with less calculations. And so this is that's one practical application, but basically the other thing I'm trying to prove to you guys is one of these terms dominates the behavior of the function as you approach positive infinity, while the other term dominates the behavior of the function as you approach negative infinity. And it's based on the two separate terms in the function itself.